This is GATE 2021 electrical question number 53. It is saying consider the boost converter shown with switch Q and operating at 25 kHz with a duty cycle of 0.6. Now under steady state condition, consider the switch to be ideal and the average resistance is asked to be found as seen from the source side. So source impedance is being asked for the boost converter. And to solve this question, we need to analyze the average source current, because this is the DC-DC boost converter for which you are being asked to find the input impedance as seen from the source side. So you are keeping your eye here and seeing the input impedance. So this is the current sent from the source side and this is the voltage. Input impedance as per Thevenin's rule is average input voltage divided by average input current. Now there is a diode and this is the capacitor and this is the load resistance. Okay, now Rin is being asked, so you need to analyze the source input current waveform like this: Is versus T in continuous conduction mode of operation. That means the amount by which the inductor is charged when the switch is closed by the source is equal to the amount of discharge that the inductor is being undergoing when the switch is open, and it is releasing the energy to this capacitor and then the load is taking the energy. So the amount by which inductor charges, same amount it discharges in every switching cycle, where this duration is d into t on. D into ts, that is the switching cycle time period, and this will be 1 minus d into ts. So in discontinuous mode of conduction, what happens? There is also one possibility that the inductor may start from here and then discharge here. So this duration, it is before reaching the cycle completion, it is discharging. So this is DCM operation, and even also possible that in the cycle it is exactly completing here, that is discharging at just the completion of the switching cycle. So this is critical conduction mode. Now we need to see out of these three which one is our operation mode, because the IS that will decide IS, and this is decided solely by the inductor value we use. So L, there is a particular threshold L critical, which if it will cross will lead to continuous conduction mode of operation. If L is less than that critical value, obviously it will not have that much capacity to store that energy and it will discharge earlier, so it will lead to discontinuous conduction mode of operation if it is our used inductor L design used, that is in this converter, is less than critical value of the inductor. So L critical for boost converter is given by d into 1 minus d whole square multiplied by RL multiplied by time period of switching divided by 2. So this is the formula you need to remember. Now coming to the solution, L critical equal to d into 1 minus d whole square RL into TS divided by 2. TS equal to 1 by switching frequency, which is nothing but 25 into 10 to the power 3, because switching frequency is 25 kilohertz, so time period is 1 by 25 into 10 to the power 3. Now delta is 0.6 into 1 minus 0.6 whole square multiplied by 10 ohm load resistance value into time period is from switching is 10 to the power 1 by 25 into 10 to the power 3 divided by 2. So L critical value is coming out to be 0.048 millihenry. Now L design is 1 millihenry, which is much greater than critical value of inductor, implies that continuous conduction mode of operation is being followed. Therefore, if we know V naught I naught equal to Vs Is, this holds true for all modes of operation. Power balance condition, that is, power should be balanced at input and output side. Now V in by 1 minus delta or Vs by 1 minus delta equal to V naught for boost converter operating in CCM operation only. So this is very important. This holds only for CCM operation. Implies that V naught can be written as V in by 1 minus delta. So V naught I naught equal to V in by 1 minus delta into I naught is again V naught by R. So this into 1 by R. V naught by R is I naught. Just replace I naught by V naught by R, then V naught square by R is coming. From there V naught value is V in by 1 minus delta whole square and by R, which is equal to Vs into Is. So V in means Vs. Now Vs square by 1 minus delta whole square. So Vs by 1 minus delta whole square into 1 by R equal to Vs into Is, implies that Vs by 1 minus delta whole square into R equal to Is. Vs is 15 volts divided by 1 minus 0.6 whole square into 10 equal to Is. So Is is, it is coming out to be 9.375 ampere. So Rs or R input source impedance is Vs average by Is average, which is coming out to be 15 divided by 9.375 equal to 1.6 ohm. So input impedance as seen from the source side of the boost converter is 1.6 ohm. This is the answer. Thank you.